3 talks for 3 research papers. And the first one is Just-in-Time Reactive Synthesis by Ilia Shevrin, a master's student at Tel Aviv University. Please, Ilia.
Hello, everybody. Thanks for joining. Good morning, good afternoon, good evening, or good night to everybody. Can you see my screen? Sorry, not yet. Now you should be able to see my screen, right? Okay,
yes,
great.
It looks perfect here.
Thank you. Okay, so my name is Ilia Shevrin. I'm going to talk about just-in-time reactive synthesis. This is a joint work with Professor Shahar Maoz from Tel Aviv University. So first of all, let's talk a little bit about the background and motivation to our work. Synthesis is an automated procedure to obtain a correct by construction system from a temporal logic specification. And synthesis is usually divided into 2 phases. There's realizability checking phase, followed by a controller construction phase. And while realizability was extensively studied and improved upon in terms of performance, construction was something that was usually regarded as a given. But empirical evidence suggests that controller construction takes a considerable amount of time and space, and according to Blom et al. And our own experience, even more than realizability checking in most cases. And also with existing construction algorithms, the resulting controller is not always the most efficient with regards to storage. Its size on disk of the output can be large. So we borrow the concept of just-in-time compilation to our domain of reactive synthesis, and we define what we call just-in-time synthesis, or JITS in short, which is I'm going to refer to it from now on. And similarly to just-in-time compilation, when parts of the code are compiled at runtime instead of before runtime, JITS similarly skips static construction step and instead dynamically computes the next states for the controller during the system execution. All of this, of course, while maintaining correctness. And our evaluation shows that overall synthesis time and space for JITS are significantly reduced with little effect on execution performance, and we will see it in the evaluation section. So we have to briefly discuss the synthesis process for the GR1 fragment of linear temporal logic. GR1 specifications consist of assumptions and guarantees that are assertions about the initial state, assertions about all states and transitions, what we usually call safeties, and assertions that should hold infinitely often in every run, what we call justices or liveness. And as we said already, the synthesis process consists of 2 phases, realizability checking and the controller construction. Realizability checking is solving a 3-level nested mu calculus formula, which we can see here, the formula in the middle. And some notation that we use is JS with index J are the system's N justice guarantees, and JE with index I are the environment's M justice assumptions. And this formula characterizes the system's winning states for the assumed guarantee game, whose formula we can see at the bottom. And intuitively, it means that as long as the environment satisfies its assumptions, and especially its justice assumptions, the system is guaranteed to satisfy its guarantees, and especially its justice guarantees. And this formula from previous slide induces the following strategy, and it also induces corresponding fixed points X, Y, and Z as intermediate results binary decision diagrams. The following strategy for the system against the environment, and we briefly describe the strategy with this diagram here. So first of all, strive towards satisfying the current justice guarantee. try to move one rank closer towards the set of states of justice guarantee J. Rank is the distance to the set that satisfies current justice guarantee, or follow iterations of Y reachability fixed point. Once justice guarantee J is satisfied, move on to the next justice guarantee in a round robin fashion, but always stay in Z or WC's set, safety fixed point, which is the winning set for the system. During the execution, the system never gets out of this set. And also at every step, check if it's possible to force the environment to violate any justice assumption J with any index I, or stay in X safety fixed point for given J rank R and I. And from this strategy, a controller is constructed. A controller is basically a milling machine, and the construction algorithm is very simple. It disjuncts all the possible transitions between fixed points according to the strategy that we've just seen into one big BDD. And this BDD is used during the execution. One step of the execution consists of the environment choosing values for the next input, after which the system chooses values for the next state or output, according to the BDD of the transitions. So we have seen the construction of the static controller and the way it is executed. We call it the static approach because there is one big BDD which is constructed statically rather than dynamically before the execution. And we're ready to present JITS and discuss its differences from this static approach. Namely, construction phase is replaced with a simple storing technique. The system strategy is migrated to runtime, and the controller itself is, in fact, never constructed. So a few words about the storing of the JITS controller. Instead of constructing the controller, we store the BDD arrays of the intermediate results. But in the paper, we show that Y and Z BDDs are derived from X BDDs. So it is enough to consider only X and encode them using three new variables J, R, and I in the following fashion into a BDD XS, which later, when the controller is loaded, each X BDD is extracted from given J, R, and I, and later we extract Y and Z, and we are ready for the execution. And we see later also that this encoding is very space efficient. So after the loading comes the execution of the controller. In JITS, as opposed to the static approach, system strategy is realized programmatically at runtime by applying operations on the X, Y, and Z BDDs during the next state's computation. So one difference from the static approach, which is now possible, is that JITS behaves eagerly. At each step, it finds the lowest rank for current justice guarantee and current rank, instead of simply trying to move one rank towards it. So instead of simply having the transition from R to R-1, we can calculate and find R minimum, so the controller can reach justice guarantee J faster. Also, when current justice guarantee is satisfied, JITS finds the lowest rank for the next guarantee, of course, staying in the Z set. And another difference is that only in the case in which current environment input does not allow the system to decrease rank, JITS finds a justice assumption that can be violated, and the system can still win trivially. This transition is only in the case in which current environment does not allow to decrease rank, and not on every step as in the static approach. So here we just put side by side the algorithm for the construction of the static approach on the left, and the algorithm for the next states for JITS on the right. So we can indeed see that the strategy is migrated to runtime, and the transitions which are encoded in the single BDD for the static construction are realized programmatically in JITS. In the paper, we also prove soundness and deadlock freedom for JITS. So let us briefly state the theorems. Let NS static be the output of next states function of the static next states function, and NS JITS be the output of JITS next states function. The output is a set of valid states represented by BDD, valid states or valid assignments for the next states. And of course, for the same environment inputs, because we want to compare JITS and static for the same inputs. And we show that JITS is sound and deadlock freedom and deadlock free, sorry, with regards to the static approach. Sound means that a valid state for JITS is also included in the valid states for the static approach. And deadlock free means that if the static approach, the set is not empty, there is at least one valid next state, it means that the JITS next states set is also not empty, there is at least one valid next state. JITS doesn't get stuck if the static approach doesn't get stuck. Now let's talk a bit about JITS extensions. So JITS decouples synthesis from system execution. Synthesis takes place at development time and runs on development machines, while system execution typically runs on very different machines, for example, on a robot. And this decoupling allows JITS to support extensions that aim to improve qualitative aspects of the execution, change the behavior of the controller, basically. And these extensions are synthesis independent, and it is possible to initiate execution of the controller with or without a specific extension and combine multiple extensions without the need to re-synthesize the controller. So we implemented several such extensions, and we briefly described a few. There is bookkeeping, which is a technique to satisfy each justice guarantee, but as quickly as possible. And this is achieved with a Boolean array that keeps track of all the justice guarantees satisfied so far. And on each step, the controller checks if any of the justice guarantees are satisfied and mark relevant bits in the array. And when the array is fully marked, it is reset, and the new round of checking which guarantees are satisfied begins. And what is important here is to observe that this behavior is not encoded in a BDD, but is realized programmatically at runtime. And it is possible with one synthesis controller to execute the controller with or without this extension and see that it may behave differently. Some other extensions that we have implemented are recovery, which is an extension that attempts to recover from environment safety assumption violation and still try to find a valid next state, for the controller. There's configurable set of justice guarantees, which is an extension that loads only a pre-configured subset of justice guarantees at initialization. And there's GR1 star, which is an extension that incorporates existential guarantees from the specification into the execution. GR1 star is a fragment of linear temporal logic. So now for the evaluation part, we implemented JITS on top of the Spectra GR1 synthesizer. And for evaluation, we consider the following three research questions. First, how does the static controller construction time compare with the realizability checking time? How does JITS compare with existing approaches during synthesis with regards to time, synthesis time, memory usage, and size of output? And how does JITS compare with existing approaches during system execution with regards to load time, memory usage, and single step time? So our corpus of specifications consisted of AMBA AHB arbiter and IBM's generalized buffer, which are known benchmarks from literature. because they are parametric and they check scalability. The largest syntax benchmarks from the Spectra website, largest in number of variables. Synthesis experiments were run on an ordinary Intel PC, while system execution experiments were run on a Raspberry Pi, which is a much weaker machine, and that was done because we wanted to simulate real execution environment, which can be totally different from the machine on which the synthesis took place. Synthesis experiments were performed on JITS versus Spectra static approach and another synthesizer named Slugs, which also works with the static approach. And execution experiments were performed on JITS versus Spectra static approach. So to answer the first question, we now see comparison of realizability and construction times. And we can indeed see that there are many cases in which construction takes more time than realizability. And we even emphasize some extreme cases where more than 99% of synthesis time is spent on construction rather than realizability checking. Now for the second question, how does JITS performs during synthesis? So we can indeed see that JITS performs very well and outperforms existing approaches with regards to construction time, with regards
1 minute.
Yes, thank you. With regards to active nodes and with regards to the size of the output on disk. Now, how does JITS performs during execution? We can also see that JITS performs very well with regards to load time, number of active nodes, and also with regards to the single step time. So to sum it up, as we said, for most specification, construction takes more time than realizability checking, and JITS outperforms existing approaches during synthesis and execution and scales better. The larger the specification, the better all the measures. Some words about future work. We want to maybe want to check if it's possible to control the trade-off between performance and memory consumption of JITS execution using BDD reordering techniques or some caching mechanisms, and also suggest different storing mechanisms to enhance configurability of the synthesized controller, similarly to the configurable set of justice guarantees extensions that we seen in one of the previous slides. Okay, so this is it. Thank you very much for listening.
Thank you, Ilia. Thank you for the talk, and there should be a round of virtual applause. And now we are ready for the Q&A. So all attendees of this session, you can use the session Q&A tab on the WOWA application to ask your question, and then we will we'll relay it to the speaker. And in the meanwhile, we have a couple of minutes. I will start with my first question is, you know, there are other approaches for reactive synthesis, not only restricted to GR1, but also, for example, to LTL. So, for example, can you apply some of the principle behind JITS, some of the concept also to other approaches like Strix, for example?
Yes, this is a good question, and we mentioned it in the paper. The approach of Strix is very different from GR1, and specifically JITS here addresses the intermediate results of the GR1 realizability checking. But the general notion of not constructing a single controller and instead dynamically compute next states at runtime can be applied even to controllers which are synthesized using different techniques than GR1, for example, Strix. So it is in fact possible to see if it is possible to use the notion of not constructing a single controller, also for approach such as tricks. But it is orthogonal to realizability checking, and this is important to understand. We use realizability checking algorithms. We do not touch them. Instead, we only address construction.
Thank you. So we have time for at least one more question. I don't see anything on the Q&A chat, and maybe the Zoomer can check if any participant has raised his hand.